Uh, may you're able to see my screen, right?
Yes, I see it.
This one? No, not this one.
Yeah, this one. Yeah, that's the one.
Oh, this is the one here. Okay.
Mhm.
Mhm.
Do we have a homework 4 or 3 is the last one?
I mean, we had an in-between one, that is, you had to do number two, but
Yeah, I'm saying, do we have
also,
a homework 4?
no, you had to do
Okay.
number two
Mm-hmm.
also with a quadratic interpolation function.
Oh, I did not do that part.
Let me re-forward that. I'm re-forwarding that to you.
So, homework 2, problem, please. Join.
I just sent to you and copied everyone else. But
Okay.
you had to also do this. But let's see this one first. Now, uh, it is saying that you can directly use the Kij, the stiffness matrix. Um, just use the final forms of the beam element equation. So let's go. I think I sent the MATLAB file, right? Or the
Yes. Yes, it did. Homework 3. Yes, you sent the model.
yes, I sent that MATLAB. So now in that, if you're able to open, let me go.
You can find it under email.
Uh, yes, but here, oh, it's actually, I think we did this very problem. So, so we actually did the whole thing in the class. Okay. So, and let me open the PPT file too. I think that also I did send in the PowerPoint, the PPT as well. So you remember, so what you do is you first mark out the global degrees of freedom. So one vertical displacement and one rotation at each element, right? U1, U2, U3, U4, U5, U6, U7, U8, U9, U10. So you have 10 degrees of freedom along the length of the beam, right? And then your stiffness matrix. Your stiffness matrix size will be 10 by 10, right?
Right.
Now you need to prepare the local stiffness matrices for each element, right? That's the first step. So that we did in the code. So here you have your EI and you have your element sizes. So first element is 6 meter in length, second is 2, third is 2, fourth is 2. Since we did not apply, like we discussed, we could even do this using 2 elements, but then we didn't do the case for a distributed moment load or concentrated moment load in the class procedure. So we are just taking 4 elements, one up to the support first element, then up to this concentrated moment second element, then here to 200 Newton third element, and there to the support fourth element. So first step would be to make the local stiffness matrices. So that is beam stiffness. We are using that code, right?
Yes.
So you just run up to there, you will see that. So you are having all of the beam stiffnesses, K1, K2, K3, K4, right?
Right.
So you can check that. So it is in the units Newton and meter. So E is in Newton per meter square, that is Pascal, and I is in meter square. Okay. So then, as you remember, you need to as you remember, now you need to complete the right hand side. So we said in the right hand side there are 3 terms that you need to evaluate. The first is the distributed load. That effect comes from this term, right? Then the integral of FW dx. So that term is there. So that term we shifted it to natural coordinate space. So integral was xc to xc plus 1. We changed the variable of integration to, instead of x, to psi, right? Then we know psi x is equal to 1 minus psi by 2 xc plus 1 plus psi by 2 xc plus 1. So dx is he by 2 d psi. So we change dx to he by 2 d psi. And now the weight function should be in terms of psi. and f also should be in terms of psi. So then we change here, substitute fx is this, right? Linear, negative 200, it goes from negative 200 to 0. Negative 200 at 0 to 0 at 6, right? Right. So that's the linear interpolation, negative 200 minus x times this by h1, 6 meter. So now in the next step, you are substituting x in terms of psi. So you change it to psi. Then you substitute xep. This is just he plus xe. So then your you will get everything in terms of he. Then finally you substitute xe is 0, is starting at 0, and he is h1. You're making it for element number 1, right?
Right.
So then you got f psi, right? 100 psi minus 100. Give me a second. I will use the rest of my computer.
Hey, good morning.
Good morning.
How are you?
We did, we know J, so we substitute J, and then so now we define the n size so that we can get so F1 is the integral of the F psi, right? Integral of F psi, so times n psi times J. That's what we are, that's the total distributed force, right? We want integral of F psi times n psi times He by 2. So we did that. Did you get it, Jimmy? So that's F1. And F2, F3, F4 are all zeros, right? F2, F3, F4 are all zeros. There is no distributed load on those parts of the beam.
Right.
No distributed load.
Yes, yes.
So now, if this is fine, like I said in the class, this is okay. No need to worry about that. You can skip that checking in the real space. Okay, next is we assemble the stiffness matrix in a slightly different way here using padding. That means what we are going to do, you know that the global stiffness matrix is 10 by 10.
Right.
And in that space, the local stiffness matrix for element 1, it should sit in 1, 2, 3, 4, because element 1 has the degrees of freedom 1, 2, 3, 4. Element 2 has 3, 4, 5, 6. Element 3 has 5, 6, 7, 8. Element 4 has 7, 8, 9, 10, right? So element 1 stiffness matrix will come here, element 2 will come here, and so on, right? So we will do each of that. So element 1, element 2, 3, and 4. Now you have global stiffness matrix, right? Now you make the padding for F2. So those are for F. So now the F1, each of those is 4 by 1, right? Each of the distribution functions, that is 4 by 1. Like what I'm saying is, for each element, there are 4 interpolation functions, right? So this we need to integrate for W is N1, for W is N2, for W is N3, for W is N4, right? Did you get it? Okay, I couldn't hear anything. But you're doing this integration for each interpolation function. So you will get your F1, I made the pad zeros, and you're inputting this into the padded one. So your F global, Janine suddenly left. Just a second. Let me, oh, you're back. Hello, Janine. Can you hear?
My internet got reconnect.
Oh, okay.
Can you hear me now? I'm back.
Yeah. So what I'm saying is the same kind of padding we are doing for the F function too. So since
Okay.
this integration should be done for every interpolation function. Now we are doing it that way. So we did it. So each of these f's for each element is a 4x1 vector, right?
Yes.
So for the first one, like you see here in this, the f1 will fit into 1, 2, 3, 4. The f for second element will fit into 3, 4, 5, 6. F for third element into 5, 6, 7, 8, and so on, right?
Right.
Okay, so that's what we did over here. So then you have your F global. Okay, and then you make your K partition matrix because now we want to solve for the unknown degrees of freedom, right? You can see here you have support at 3, roller support, and fixed support at node 5. So degree of freedom number 3 is 0 since it cannot move up and down, and degrees of freedom 9 and 10 are 0. So you know that U3 is 0, U9 and U10 are 0, right? Okay.
Yes.
So you only have U1, U2, U4, U5, U6, U7, U8, right? Okay, so see this is for 1 to 2 and 4 to 8. 1, 2, 4, 5, 6, 7, 8, right? So your
Right.
partition matrix is extracting that out of the global stiffness matrix. Then this is your P partition, the total concentrated loads, that is this vector, this vector, and the total concentrated moments. We wrote down all of that. It's 0 for all. At R3, you have the reaction at 3, then you have reaction at 9, and then you have a concentrated load of 200 at node 7.
What's that?
That's negative 200. Then for moments, you have the moment at support at node 5, then you have concentrated moment at node 7. So you node 4. So you have at 7, you have at 8 a negative moment of 100, and then you have the reaction at the fixed support. So that is P, that is M. And when you're taking out 3, 9, 10, your only things will be 0, 0, 0, 0, 0, 0, negative 100, negative 200, 0. So when you for P this is then for moment only the negative. Then your F part you have already from F global, same way you partition. Then make a small F part in which you add the distributed load, then you add the concentrated forces and concentrated moment. And then you find out your displacements as inverse of K times F, right? So those will give your unknown displacements U1, U2, U4, U5, U6, U7, U8. So you have those. Now you assemble that into your global displacements, right? And in your total displacements. You found out just now from line number 81, the calculation. From the calculation at line 81, you got your U1, U2, U4, U5, U6, U7, U8. And now you plug that back into the total displacement vector. That means you need to include U3, U9, and U10 also. So you include that in between U3 and U9 and U10. Now you have your total U. You can do K global times U is the force global, right? Then F global was having F1 plus F2 and F3 and F4. You take out those, then you get the reactions, right?
Right.
And I think we said just up to here is sufficient. So here is the reactions. Then we just verified that the force equilibrium and moment equilibrium. That we did, I think, on force equilibrium was satisfied. You can take the total force due to this 200 distributed load and the 200 Newton. Then you can compare that to reactions at 3 and at node 2 and node 5. So it will work out. And we also did sum of all moments at node 1. We were getting 0. So that completes the problem. Actually, we have done the whole thing in the class.
Okay. Yeah, thank you so much. I was still watching the recordings. That's why I wanted you to go over.
Sure. We did the whole thing. Yeah.
Oh, and appreciate you so much.
No problem.
Thank you so much, Doctor.
You're welcome.
Is the MATLAB code you using the same one as you sent?
In the same email. Yeah. You just need to put all your codes into one folder. That's
okay. Sounds good. Thank you so much.
Amira, I have a request. So if you don't have any immediate question, I will come back. Maybe I need to. Janine, you had another question.
No, it's just the second part of homework too, but we can't wait. I was going to ask, where are you going to put this recording? On the
no, this is recording to my computer.
So are you going to send it to our email? Can you send it to our email? Or maybe...
just a second. Amira, the work is just know what me and Janine discussed. So it's the same thing. Janine, the recording I will put on YouTube because it is recorded locally to my computer. So I will put it on YouTube.
Can you send it the link to our email?
Yeah. I will send it. Yeah.
Sounds
good. Amira, you have to go, is it? Okay, no problem. Homework 3 is the one I emailed here. It's just now me and Janine discussed the whole thing. Is for beam. We didn't get to frame this time. It's just the beam. That's the last one. This is what I had sent out. And just now we discussed the whole thing, me and Janine. So I will put this recording. Okay. Let me